Yes, civil engineering students and structural engineering students. Today we will be seeing about the constant strain triangle. So you can see that as the figure represents, this triangle is called constant strain triangle because wherever the strain values you are calculating inside the triangle, it will be equal to one another, or they will be constant throughout this triangular element. Okay, it is because the shape functions are linear. So proceeding further, you can see that here Q1, Q2, Q3, Q4, Q5 and Q6 are the nodal displacements at the particular nodes 1, 2 and 3. And x1, y1, x2, y2 and x3, y3 are the Cartesian coordinates for the particular nodes. And this whole triangular element is taken as a constant strain triangular element. And inside the particular point, you can see that the nodal displacement is mu and v. So what is u and what is v? That could be found from the shape functions. So let us see the basics of the constant strain triangle, starting from the basics and also explanation on shape function. So proceeding further, this is said to be finite element triangulation. That is, you are going to split a particular domain into lot of triangles, and these triangles can be solved individually by applying finite element methodologies and boundary conditions. And finally, you will get the values of the displacement, stresses and strains for all the triangles. And this is the basis of finite element method, where you are following the triangulation. It is said to be finite element triangulation on a particular domain. For example, if you take any of this triangle, for example, if you take this triangle as one, so it could be taken outside and you can solve this triangle using the principles of shape functions and applying boundary conditions. Now, constant strain triangle. What's a constant strain triangle? It is nothing but a finite element in which the shape functions are linear over the element. Note that the shape functions are linear. They are not non-linear, they are linear. Because the shape functions are linear, the strains computed from the displacement field are constant over the element. Suppose you take this particular element, the strain is represented by epsilon p. So this epsilon p is equal to constant. Suppose you take another point, it is epsilon q. So this is also constant and equal to epsilon p. Now, where do you get this strain? You are getting the strain from the displacement field. So that the displacement field is u and v. And basically in finite element method, whatever you are doing, you will be computing the values of displacements such as u and v, and you will evaluate the strain and evaluate the stresses. The ultimate aim of the calculations is to evaluate the displacements, evaluate the strains and evaluate the stresses. So all these kind of things are evaluated in finite element analysis. In particularly in constant strain triangle, as I told you earlier, the shape functions are linear, and because the shape functions are linear, the strains computed from the displacement field are constant throughout the entire triangle. They do not vary from point to point. So that's why it's called constant strain triangle. Now, what's the shape function? In context of finite element analysis and the finite element method, a shape function is a mathematical function used to interpolate a solution. That is, the solution could be displacement, temperature and pressure, or even hydraulic gradient. So this is said to be shape function. So shape function is nothing but a mathematical function, which is also known as interpolation function, which is used to find out the solution such as displacement, pressure, temperature, stresses, strain, whatever it may be, and based upon the nodal values. So for example, you are designing a triangular channel here. For this triangular channel, this is point, at this point you have a hydraulic gradient phi 2, and at this location you have a hydraulic gradient phi 1, and at this location you have a hydraulic gradient phi 3. Now, based upon the nodal values, you can find out the hydraulic gradient at any particular point inside the constant strain triangle. So that's what we are trying to make, and these could be done using the shape functions. Now, if you use the same shape function for all these parameters as well as the geometry is represented by Cartesian coordinate. If you use the same shape function for geometry as well as the hydraulic gradient or any field variable, that is said to be isoparametric formulation. So what is isoparametric formulation? Is nothing but same shape function is used for defining the geometry in Cartesian coordinate as well as the field variables such as displacement, temperature, hydraulic gradient or pressure based upon the nodal values of the element. So now we will represent the shape function on these 3 points as n1, n2 and n3. Okay. So what are all these shape functions? So here you can see that the value of n1 equal to 1 at this particular location and the value of n1 equal to 0 at the other locations. Similarly, if you take this element, the value of n2 equal to 1 at this location and n2 reduces to 0 at these locations. Similarly, if you take n3 is equal to 1 at this particular point and n3 equal to 0 at the other locations. So here n3 equal to 0. Now you can see that we have also represented the element by using other coordinate systems such as psi equal to 0. So this axis is psi equal to 0 and this axis is psi equal to 1. Now similarly you can see that other axis is eta equal to 0 and here you have eta equal to 1. Similarly you can represent the same thing for the other shape functions also. So what are all these psi and eta? They are nothing but the natural coordinates. So now we are having two coordinate system which is said to be Cartesian coordinate x and y and also other coordinate system which is said to be natural coordinate system which is represented by psi and eta. Now this is a typical example where you are having the value of n1. So this is the point where the value of n1 is we are trying to find out the value of n1 at this particular location where the Cartesian coordinate is x comma y. Now similarly you can see that the psi equal to 0 axis and psi equal to 1 axis and eta equal to 0 axis and eta equal to 1 axis are represented here, and basically we derive a relationship between all the three shape functions, that the shape function n1 plus n2 plus n3 is equal to 1. So this is the relationship between these two shape functions which have been derived. Now look at this tetrahedral element. You can see that this is the point 3 and opposite to the point 3 this area is A3 and opposite to point 1 you have another area which is said to be A1 and opposite to point 2 you have the area A2. Then what is the area A? A is the area of the triangle 1, 2, 3. A is the area of triangle 1, 2, 3. And we get a good relationship between the shape function n1 and a1. Shape function n1 equal to a1 upon a and n2 equal to a2 upon a and n3 equal to a3 upon a. Where a is the area of the element, the area of the triangle 1, 2, 3. Now we get a relationship between these areas and the shape function. Now you can see that how we are going to relate the shape function with the natural coordinates. We represent the value of shape function using natural coordinates by this relation. Let n1 is equal to psi, n2 is equal to eta, and n3 is equal to 1 minus psi minus eta. So this is what we call the relationship between the shape function and the natural coordinates. If you add all these three equations n1, n2 and n3, finally you will have this relation n1 plus n2 plus n3 equal to 1. Now isoparametric representation. What is meant by isoparametric representation? If you use the same shape function for the geometry, which is the Cartesian coordinate xy, and if you use the same shape function for field variable, so we can write down it as field variable. So if you provide the same shape function for geometry and field variable, you can see that those type of representation is said to be isoparametric representation. So you can, for the field variable here is the displacement q. So you can see that we are using n1, n2, n3 for defining x1, y1, x2, y2, x3, y3, and also we are using the same shape function n1, n2, n3 for defining the unknown displacement field. So this formulation is called isoparametric representation. Isoparametric representation in the sense you are using the same shape function for the geometry as well as for the displacement or any other field variable. So if you use the same shape function, that is said to be isoparametric representation. So here let us take this constant strain triangle. Now we will solve a simple problem upon that. Before that, you can see that this is the equation represented for calculating u and v. And if you substitute this n1 equal to psi, n2 equal to eta, and n3 equal to 1 minus psi minus eta, we will substitute in these two equations and we will compute in this tabular column. We will substitute these values in the tabular column. And finally, you are getting u equal to psi times q1 minus q5 plus eta times q3 minus q5 plus q5, and v is equal to psi times q2 minus q6 plus eta into q4 minus q6 plus q6. Now you can see that the values of u and v are obtained from the matrix q1, q2, q3, q4, q5 and q6. So if you know these nodal displacement and if you know psi and eta, the natural coordinates, ultimately you can get the value of u and v, which is said to be the unknown existing inside the triangle. For example, inside the triangular element, at this particular point, you want to calculate what is u and what is v. So this could be found by using this psi, eta and q1, q2, q3, q4, q5 and q6. Now we get a relationship u equal to n into q. From this equation we get u equal to n into q. What is n matrix? You represent the n matrix like this: n1 0, n2 0, n3 0, 0 n1, 0 n2 and 0 n3. Then you can multiply the n matrix with this q matrix. Ultimately you will get u equal to nq, where u equal to u and v, or u and v1, whatever it is. Now, I told you about isoparametric representation. Here, you can see that we are using the same shape function which was used for finding the displacement. What are the shape functions? n1, n2 and n3. What do you try to find here? You are trying to find out what is x and what is y. Now, you are using the same shape function for find about the Cartesian coordinate x comma y, as well as for the displacement field q1, q2, q3, q4, q5 and q6. So this type of representation is said to be isoparametric representation and isoparametric formulation. Then again you substitute the natural coordinates in these equations. You substitute the natural coordinates, you end up with this equation: x is equal to x13 psi plus x23 eta plus x3, y equal to y13 psi plus y23 eta plus y3. So what is this y13? I will explain only one component. y13 is nothing but whatever you obtain as the difference between the y1 component and y3 component. y1 coordinate and y3 coordinate. Suppose if you take x13, what is x13? x13 is nothing but x1 minus x3. So you can see that we find out the Cartesian coordinate x comma y, that is at a particular point inside the triangular element. So at this point P, the variables are x comma y. So this x comma y is obtained by these two equations, which are connected by x1, x2, x3, y1, y2, y3 and the natural coordinates psi and eta. Now let's solve a simple problem. you compare these two diagrams, we are going to estimate the shape function for this particular point P. We want N1, N2 and N3 at the interior point P given by the following figure. Here X1, Y1, X2, Y2, X3, Y3. Here you can see X1, Y1, X2, Y2, X3, Y3. And the nodal displacements are Q1, Q2, Q3, Q4, Q5, Q6. We are not asked to find out what is the value of U and V, but we are only asked to find out what is the shape function N1, N2 and N3. Now, here you can see that the equation is X equal to X1 3 psi plus X2 3 eta plus X3. Now, we know that X is equal to 3.85, that is given. The X value is given here. X, this is X comma Y. This is X comma Y. And other things are X1, Y1, and this is X2, Y2, and this one is X3, Y3. Now, using these data of Cartesian coordinate for 3 nodal points and the Cartesian coordinate for a particular point inside the triangular element, we are able to find out the values of N1, N2, N3. So first let us take this equation X equal to X1 3 psi plus X2 3 eta plus X3. Substituting the values of X1, X2, X3, you end up with this equation X equal to minus 2.5 psi plus 3 eta plus 4. So this is obtained from this. These calculations yield this equation. Similarly, we know that Y equal to Y1 3 psi plus Y2 3 eta plus Y3, and we know the coordinates of this Y1 3, Y2 3, Y3. Then on substitution of these values in these equation, after the calculations, you substitute it here, and from this you are getting this equation. Now you have got two equations. What are all the two equations? You have got the equation number 1 here, and this is equation number 2 here. Two equations, two unknowns, solve them. Finally, you will get what is the value of psi and what is the value of eta. So how to solve these two equations? As you know, it's a simple thing. Now you can see that this is the equation taken, and this equation is divided by minus 2.5 on both the sides. So this equation is rewritten here, and from this equation you are getting minus 1.5 equal to minus 2.5 psi plus 3 eta. So on simplification, this is the equation number 3. Now similarly, this equation is simplified here, and on simplification we are getting the equation number 4. Now you can solve the equation 3 and 4, two unknowns and two expressions and two unknowns. And from this you will get the value of psi and eta. So what is the value of psi? The value of eta is equal to 0.2. So N2 equal to 0.2. Obviously N2 is equal to 0.2. Now substitute this eta equal to 0.2 in this equation. So you can get 0.06 equal to psi minus 1.2 into 0.20. From this again, after simplification, you get psi is equal to 0.3. So you can see that N1 is equal to 0.3 and N2 equal to 0.2. And we know that N1 plus N2 plus N3 is equal to 1. So using that, we come again with N3 is equal to 1 minus N1 minus N2, which yields 0.5. So this is how we estimate the value of shape function for the constant strain triangle given in the problem. If you have any doubts, you mention in the comment section. Thanks for watching. Thanks a lot.